This video gives an overview of the two types of encryption available on the internet: symmetric encryption and asymmetric encryption. First of all, we need to know what is meant by the word encryption. Encryption is an algorithm. There's lots and lots of different types of encryption algorithms, but their purpose is the same: to turn plain text into ciphertext. Cipher down here can be spelt with an I or a Y. It means the same thing. Plain text is the original readable document. It can be read by anyone. The ciphertext, however, is the scrambled form of that plain text. In other words, if a hacker intercepts an encrypted message during transmission, that hacker won't be able to read the ciphertext. There are two main types of encryption that we need to look at, both symmetric encryption and asymmetric encryption. The simpler of the two is symmetric encryption, where basically we have a single key used to both encrypt and decrypt the message. The problem is, if Bob wants to send the message to Alice, he also needs to send the key to Alice so that she can unlock the message or decrypt it when she receives it. This is known as the key distribution problem, because what happens if the key was intercepted during transmission? The hacker not only has the data, but the hacker also has the key to unlock that data and read it. The solution is seen here with a little arithmetic trick using modulo division. Both the sender and the receiver think of a secret number. So here, for example, the sender's secret number X is 2 and the receiver's secret number Y is 4. They both put their secret number through the same algorithm. 7 to the power of X mod 11 versus 7 to the power of Y mod 11. We can see for the sender that 7 to the power of 2 mod 11 is 49 mod 11, giving us 5 as the remainder. 7 to the power of 4 mod 11 gives us 2401 mod 11, leaving us 3 as the remainder. At this point, both the sender and receiver transmit their calculated value, not their secret value that they originally had. So, the sender transmits the value 5, the recipient transmits the value 3. Then finally, in step 4, we use the same algorithm, just substituting 7 with the number that was calculated and received by the other person. So here the sender is 3 to the power of X, or 3 to the power of 2, the original secret value, mod 11, which is 9 mod 11, giving us 0 with a remainder of 9. Over here by the recipient, we have 5 to the power of X, mod 11. So I'll just switch that there. 5 to the power of 4, 4 being the recipient's original secret number, mod 11, which is the same as 625 mod 11, giving us 9 as the remainder. So now the original secret numbers, 2 and 4 respectively, are not sent. However, both sender and recipient end up with the same value, or key, 9 in this case, that is used to encrypt the message from the sender's end and decrypt the message from the recipient's end, all without actually sending the key. The more advanced form of encryption is asymmetric encryption. In contrast to symmetric encryption that only uses a single key to both encrypt and decrypt the data, asymmetric encryption uses two keys, a public key and a private key. This is also why it's sometimes known as public key encryption. One key is used to encrypt the data, often the public key, and the other key is used to decrypt the data, often the private key. So in this example, Alice wants to send an encrypted message to Bob. So Alice requests Bob to send her his public key. The public key is known to anyone. It doesn't really matter who has it. And he obliges. Alice then encrypts the message, not with her own public key, but with Bob's public key, before sending the message. When Bob has received the message, he decrypts the key with the corresponding private key, his private key. Only Bob knows his private key. So therefore, only Bob can decrypt the message. And that's essentially asymmetric encryption. One key is used to encrypt the message, another key is used to decrypt the message.